We are now going to talk about the specific heat of ideal gases, which is similar but different from when we talked previously about the specific heats of liquids and solids. So one of the big things that makes this different is that it's process dependent. For solids and liquids, we just heated them. We didn't worry about work. We didn't need to change their volumes or their pressures because they're liquids and solids. They don't change volumes, but gases do. So let's think about two different processes by which we have an initial temperature determined by this isotherm and a final temperature determined by this other isotherm. We obviously can go from this isotherm to that isotherm in a lot of different ways. But the two ways we're going to look at are a constant volume process, where we go straight up, isochoric process, and a constant pressure process, where we go horizontally, an isobaric process. Now, the amount of heat transferred in each of these is actually different, but the delta T is the same. And the number of moles would be the same if we're talking about a well-contained ideal gas that has the same initial state in each case. So the Q is determined by two different equations, and note in this case we're using the molar specific heats. So for the liquids and solids we had both a normal specific heat and then a molar specific heat. For ideal gases we only work with the molar specific heat. So why would this be? Why would we have two different heats resulting in the same temperature change? Well, obviously the work is different here. So we're going to come back to that, but definitely, start by thinking, and we kind of need to look at these two slides together. We have two different equations that relate to the same gas going from one temperature to another in two different processes. Well, so how did we get those values of C for liquids and solids? We look them up in a table. It's basically the same now, except when we look in a table, we're going to separate out the monatomic gases and the diatomic gases. And note that our values for CP, which refers to the constant pressure processes, and CV, which are the constant volume processes, again, those are our equations here. So P for pressure, V for volume. Note that these are the same. Helium, neon, argon, same ones. Now for the diatomic gases, they vary a little bit, but for the extent that we're being physicists here and saying these are ideal gases, we basically say they're the same. So they're effectively the same across similar gases, right? So the monatomic gases are similar to each other, the diatomic gases are similar to each other. In the next chapter, we'll actually learn a little bit about why they're different from another, but right now that doesn't matter. The other thing to notice is that Cp minus Cv is actually a fixed value, and this is the same for both monatomic and diatomic gases, and this is the ideal gas constant if you check the units. So this is really interesting, and the book goes through some detailed mathematical reasons why that I'm not going to go through here. Again, really what this comes down to is processes, and I think that it overcomplicates it in a way, and I would present this material a little bit in a different order. But the main thing to think about is work, right? Think about this constant volume process. No work is done. But in this constant pressure process, there is work done. So if we actually wanted to relate our thermal energy to what's happening here, our thermal energy in this constant volume process is only determined by Q. Our thermal energy in this constant pressure process actually involves both work and Q. So when you think about it that way, it isn't surprising that in fact these are two different equations. Because if we think about the change in thermal energy, which is related to temperature, in this case, we have to worry about work for the constant pressure process, but not for constant volume. So Q, heat, can't be the single predictor here because we do have to think about work. So I think these equations in a way are a little bit silly. If you need one equation to rule them all, it's this equation. This is true for any ideal gas process. And the book does the derivation, but effectively it comes from this first one, this constant volume equation, right? That this constant volume equation, we know no work is done. And so there, E thermal, the change in E thermal is equal to Q, which is equal to this. But we've been saying this entire time that thermal energy relates to temperature. And if you remember back to the equation for solids and liquids, it basically looks like this. So I think that that's the easiest way to approach this entire section. Start by looking at this equation and saying that, okay, heat is going to give me a proportional temperature change, and in this process I've done no work. Saying that, okay, heat in this case is my thermal energy change, and then basically say, well, for any other process you have to think about work. So that's, I think, the most straightforward way to think about it. You're free to use this equation for constant pressure, but it really is just a simple calculation that's kind of coming from these other things. You could derive this if you know these other two. That would work. So this is really, I think, the main takeaway. For any ideal gas process, the change in thermal energy is going to be equal to the number of moles times the constant volume molar specific heat times delta T. Because again, in a way, this is the quote-unquote pure one. One thing that I want to mention, my subscripts here sometimes vary from capital to lowercase. That's just on accident because I can't always see when they're small which one I've typed. So constant volume is the best one to use. You can use that, and that will give you the change in thermal energy, which is equal to Q, if in fact no work is done. So what we've just found, in a way, in a very roundabout way, is that heat depends on path. And again, if you understand work and the first law of thermodynamics, this shouldn't be surprising. Think about this PV diagram where you have an initial state and a final state, and we've connected it by two different paths. Now you might want to say, hey, these are actually the same because one is constant volume and one is constant pressure, but not actually. Let's think through this. So we know that our final and our initial temperatures are defined. That means that our change in thermal energy is defined, because again, change in thermal energy relates to temperature. So now we know that work is calculated from the integral. It depends on the path, right? So look at process A, which goes horizontal and then vertical, process B that goes vertical and then horizontal. Obviously, those are going to have two different integrals under them. So we know that the work done to go from I to F is going to be different if you've done A versus process B. And from the first law of thermodynamics, we know that the change in thermal energy is equal to work plus heat. So, of course, Q, our heat, must depend on path. Because if it didn't, there is no way that the thermal energy could be the same between I and F, and we could have different work done on these paths. So Q depends on path, work depends on path, change in thermal energy depends on work plus Q, and change in thermal energy depends only on initial and final temperatures. So again, we're bringing a lot of ideas together. It's not circular, it's just self-consistent, and you can get to the same ideas in a lot of different ways. We can talk about ideal gas processes and PV diagrams. We can talk about the first law of thermodynamics, relating work and heat. The piece that really requires us to bring it all together is when we talk about heat on PV diagrams. We don't directly represent heat on PV diagrams, but there is heat entering or exiting our system in many processes. So that's why this suddenly gets complicated with the introduction of heat, but otherwise we can't fully talk about the change in thermal energy.